We go to another topic in this session, and we concentrate now on radars. And the first is about the EISCAT Meteor radar, the atmosphere and geospace radar, current status and science outlook for meteors. Go ahead.
Thank you. So my name is Johan, Kero, and I come from the Swedish Institute of Space Physics in Kiruna, northern Sweden. And I will show the final construction phase of a new radar project called EISCAT 3D. And of course, I would be very happy to invite Svetlana and Irina to collaborate with us using this radar in the future. It's an international research infrastructure, and it's available for peer review programs as well as the countries who have been contributed with funding. So let me just show a quick drone overview of what EISCAT is. And this is a film. Allows in the future. So to go back to this, this is what I wanted you to pay attention to. Here we have actually a prototype called the PET, and it was used in Kiruna for 5 years in order to test the signal processing algorithms, and now it has been moved, of course, away from there. And this particular antenna itself will be unfortunately removed during the coming year because it was constructed in the late 70s, inaugurated in 1981, and it's now no longer mechanically stable, so we will unfortunately have to remove it. But how did EISCAT all start? Just to give you an impression. So in the 1960s, the countries, Sweden, Norway, Finland, UK, Germany, and France, they decided that it would be a good idea to have an incoherent scatter radar in the auroral zone. And why in the auroral zone? So there are already other radar systems at lower latitudes, but at that time there was a lack of observations in the high latitude region where a lot of interesting physics occur. So this is kind of this is a more modern picture than the 1960s, but it doesn't contain a meteor, and actually they didn't have meteors in the original science case. EISCAT was formed in 1975, so it will have its 50-year anniversary next year with a symposium in Kiruna. And this was its first council meeting in 1976. This was our director at the time, Bengt Hultqvist. And they decided on how to construct, first of all, the radars in Kiruna, Finland, and Norway. So it's a tri-static system. I will show some data from that later on. Later on, they also constructed another 120 times 40 meter sized parabolic, well, cylindrical dish antenna, and in addition, a system on Svalbard. So the Svalbard system will hopefully continue to operate, while the mainland systems will be replaced by EISCAT 3D. So as you saw, the member countries have changed throughout time, and so has the institutions that use the data. And this small map just shows which institutes have been using EISCAT data for different publications. And as you see, it's really a worldwide collaboration. So 20 years ago, when I was a PhD student, I was part of a user survey. So what do we need for the next generation radar system? And this was part of, the EISCAT got funding together with a set of universities and also the Swedish Institute of Space Physics to perform a design study for the new radar system. And you see, these things take time, so it's 20 years ago. And after some 6 years, it actually entered the European Research Infrastructure Roadmap, which was helpful in the sense that it shows on a European level that we think that this is an important research infrastructure, and that helps coordinate funding. So actually from 2009, we've had user meetings in Uppsala every year. And these user meetings, they somehow were more active in around these years, because that was at the time, 10 years from now, when we actually were trying to convince our funding agencies to fund the new system. And I was leading the Swedish consortium, and in 2014 we actually got, well, partial funding for a new system. And what we had agreed upon in the user community was that the old mainland systems would be replaced then by something what you saw in the pictures. It would be, at this time we thought about a 5 megawatt pulse transmitter, 233 megahertz operating frequency, 3 phased array sites, and so on. It will, in addition to the big antenna that you saw, it will have outrigger subgroups to make in-beam interferometry, dual polarizations, and so on. And this was the artistic impression, and you see it was quite similar to what we actually can see today. But in order to do this, of course, other EU projects were needed. So there was a preparation for production EU-funded study where actually these prototypes were built. And then in 2017, the real construction started. And it should have been finished by now, but it's not yet. So typically for these research infrastructure projects, they will have some delays. So we hope that by next year, we will see the real first light. So what are we actually looking at here? This is now northern Scandinavia, and the old systems, they were located now in Tromsø, Kiruna, and Sodankylä. They will be replaced now by EISCAT 3D, which has a more symmetric distribution of sites, about 120 kilometers in between. Transmitter in Skibotn, and then 2 sites in Finland and Sweden. And as you say, EISCAT headquarters itself, where most of the staff are, it's located in Kiruna at our institute. And the sites, they will not be on the internet. They will have their own wavelength in the fiber system of the Nordic countries. So all data will go to a data center in Kalix via dedicated fibers. And what we currently end up with, it's almost what we wanted in the first stage. It's slightly reduced pulse transmitter power. It will be 3.7 megawatt. And we have 5,000 elements at the remote receiver sites. And probably we will not be able to run continuous operations. We had the plan that it should run in a kind of standby mode, in a low power mode. And whenever geophysical conditions are good, meteor showers, one of them, one could increase the duty cycle tremendously. Now it seems like probably the radar will be turned off from time to time unless we get more operational funding. And multi-purpose experiments, of course, we hope that we will be able to piggyback meteor observations whenever the radar is running. And this is yet to be seen because the experiments are not there yet. So as I mentioned, this is now the main array in Tromsø, and the central part of this is equipped with transmitters. So actually, if one would equip all of the antenna elements with transmitters, one would have a 10 megawatt pulsed peak power. Here is one of these outrigger subarrays, which is quite close to the one, and you might see some other one, but there is 10 of them and up to 1.5 kilometers away. And in addition, of course, to the antennas themselves, which we see, there are under each subgroup of 91 antennas, we have a container which contains then the transmitter, receiver equipment, and pulse control units, and so on. So, to go further into meteors, earlier talks have already mentioned radar observations, mainly the trail echoes, and with high power large aperture radars like this, what we typically see is the meteor head echoes. So we penetrate into the deep, dense plasma of surrounding a meteoroid, and we can get very accurate time of flight measurements and Doppler velocities of the targets. Now, EISCAT 3D will be able not only to address the actual meteor itself, it can also be used for ionospheric physics, which I will not go into here. For example, studying sporadic E layers and to study persistent trains and so on. Now, just for those of you who are not so familiar with high power large aperture radars, they are the basic result of having a very big dish or having a very large aperture of small antennas is practically the same. You can concentrate your transmitted power and your sensitivity into a very narrow beam, which is typically of the order of 1 degree. And with the old EISCAT system, which I used extensively while it was operational as a tristatic system, one could then point these parabolic dish antennas towards a common volume and look at what is happening there. And we saw earlier that fragmentation is one of the processes that you can study. And you can also get then, this is now just velocity components seen at the 3 different receivers. You typically only see a short part of the meteor itself. You only detect it for 1/10 of a second because your observation volume is very small. With EISCAT 3D, instead, you're able to actually spoil the beam to make it wider, or have several transmitter beams intermittently and have simultaneous receiver beams along the transmitted beam so that you actually illuminate a larger volume. You can see the start and the end of the meteor, which will be very helpful. Otherwise, the data will practically, we will get 3 components again. Now it will be Karesuvanto, Finland, Kastinen, Sweden, and Skibotn, Norway. And we can combine those to get meteoroid velocity curves for all detected meteors. And if we have not a low power mode where we could perhaps only transmit 1 or a few pulses per second as a monitoring mode, in that case, we would only get 1 of these velocity data points. We would not get the time profile of a detected meteor. When the radar is running with a high power mode, we would get the full velocity profile. And of course, we will want to combine such information with ablation models to estimate mass and look at ionization and so on. And we will get this for hopefully many thousand meters per hour when the radar is operating in full power mode. And one interesting other thing one can do, in addition to these precise orbit determination, is that we can study the scattering aspect dependence of meteor head echoes. So we will actually see the same plasma from different angles. One is a monostatic case, and then we have 2 forward scatter geometries from the same meteor. And now this is a map again showing northern Scandinavia. So in addition to the EISCAT 3D system, there is also a radar on Andøya called MARSI, operated by the Atmospheric Institute in Kulungsborn. And it is operating at a lower frequency, 53 megahertz. And it will actually be possible to make common volume measurements with MARSI and EISCAT 3D if we will just point the beam in a common volume. And MARSI, as said, it's 53 megahertz. It's also a phased array antenna. And we have already used the current EISCAT parabolic dish antenna and MARSI to make common volume measurements. And this kind of information is important for constraining scattering models and better understand how one can estimate meteoroid masses from head echoes. So before, I could just say, that I will leave this summary on. I see I have few seconds left here. I could just say that, as you saw, it takes 20 years to build a radar in Europe. Now, China was also part of EISCAT and is part of EISCAT. They have a different financial system. So 5 years ago, or a little bit more maybe, they decided, okay, why don't we build our own EISCAT 3D system? And they call it Sanya, and it's actually now already operational. It's slightly smaller than EISCAT 3D, and it's operating at 440 megahertz and so on, and it's located at a lower latitude. And this will be very useful actually, because now you see this is a map of high power large aperture radars which used to be in operation in 2019. And here you can see, for example, the Meteor radar. Sanya is not on this picture here. EISCAT is located at a completely different latitude. Arecibo is already gone, and so on. So it will be very useful to have two tristatic systems so that we can actually get independent confirmation of processes that happen, and also meteors at the low latitude as well as high latitude. Okay, I can leave the summary on and open for questions. Thank you.
Thank you, Kero. So we have time for one question. No questions. Impressive here. Sis.
Thank you. It's very impressive, but I wonder. So, how do you manage to how do you say that? How do you? Shit, the word escapes me. But the weather well, there are weather elements and so. And how do you keep it up to date? How do you? Forget the word.
You're talking about the actual radar itself.
Maintain it.
Yes.
How do you maintain it with all the elements of the nature there?
Yeah. Now this will be up to proof, of course. We can see, for example, that this MARSI radar here, it has been in Andøya at a very similar latitude, and it's actually out at the Atlantic Ocean, where you also have salt water and so on. So it will be dry over there compared to what we see at Andøya. So I hope that this will not pose a problem. And the PET array has survived for quite many years, and that's a complete subarray with 91 antennas. So we don't think that would be a problem. Thanks.